common topic of signal and system. Uh, Basically, it deals with very mathematical formulas, but I will try to keep it in a more generalized form so that we may, for the time being, left aloof the mathematical part. Okay, signals as such can be dealt with anything that is related to a perception of vision or a feeling. It can be signal from a sensor. It can be signal that is received by human eye. It can be a signal that is received by a telescope or a periscope. It can be anything that creates a visual or sensory perception. Now, as per his first slide, I have here shown a very generalized view of a generalized system in which there is a particular input and there is a particular output signal. Input is shown in a one-dimensional way, where amplitude and time are shown. System can be anything which manipulates or transforms this given input signal, which we can see here clearly that input is a given this thing and output is an modulus of this function in which a negative portion are clearly clipped. Now a very practical image is being shown in which clarity is being assessed by a single white granules which creates a high contrast. But that is a practical thing. We will deal with it later. Now moving on to next slide. This is the whole summary in which signals are being classified and systems are being dealt with. In a starting part, signal classification and representation are there, which are further classified as types of signals, their basic sampling and quantization theory, which will deal when we deal with digital communication systems. Now systems are being dealt here, being modified or being generally studied. So when we are only studying, not modifying or changing, linear time invariant system is being shown in which three main parameters or criteria is being discussed: time and frequency domain, impulse and stability. Now there is a processing part which is being shown by digital filters and related mathematical tools which helps in digital filter designing. Now we return to a very basic question. Now, instead of going directly to the mathematical part, first we just want to know that are signal just signal, or signal can be classified in one-dimensional, two-dimensional, or even three-dimensional being. Now here I have using a sets trying to classify signals in terms of 1, 2, and 3 dimensions. A little bit of mathematics is shown, which here shows state space analysis, in which the first part is one-dimensional, in which time and space is mentioned. Now, in second part, x1 and x2, which mainly deals with length and width, and three-dimensional, in which three variables are there: depth, width, and height. Now, practical examples are hereby mentioned, which shows one-dimensional. For example, ECG we do commonly in hospitals, and we see a printout report. Basically, a one-dimensional signal. Voice we speak in pictorial form is a one-dimensional, and music will represent is a one-dimensional. Now, image has length and breadth. If we take a printout on a piece of paper, that will be deal with length and breadth. Same way, video sequences. Now, if we are dealing with three-dimensional data, then three variables will be implemented: length, breadth, and height commonly. Now here we are shown a practical representation of a one-dimensional signal, which is a AZC signal. One-dimensional, mainly we mean by that, we can show a particular variable with relation to a time. Its width we cannot show. In here only we can show its height variation with time. Here we can see that on X interval it's time, and on Y interval it's the signal amplitude. So one-dimensional signals mainly can show the relation between a particular variable. It can be width or it can be height, but only it can be one variable with respect to time. Now this is a biological signals EEG graph, and same way many ECG graphs are there. Now here we are showing a two-dimensional signal. Example here is taken is the MRI scan, in which we can clearly see a particular diagram which is shown. It can be shown in terms of length and it can be shown in terms of width. In here, the third variable, depth, we cannot see the depth of any particular diagram. For example, here we are seeing an MRI scan of a brain, human brain, in which length, for example, if we see the top view in the first diagram, this is the side view and this is the overview. So at a particular time, length and breadth, because in a particular figure, only two magnitude variation can be shown with respect to time. In the same way, LED display of lights is also a two-dimensional representation. Now we introduce a little mathematics in here. Now we have related one-dimensional, two-dimensional signals in terms of variables, independent variables and dependent variables. Here we are taken X as an independent variable and Y as a dependent variable. It can be function of time or it can be function of distance, in which here it is clearly mentioned is the form of function. Then X variable is an independent variable, which in turns create a dependent variable time in one dimension and so on in two dimensions. Now image is always shown in terms of two dimension or three dimension. Now a little scale up of mathematical dimension is there. For example, now function is not just of X, but function is of X and Y both, and it's related with respect to time. Always in imaging or in diagrammatic or in a signal representation, magnitude can be in three dimensions, one or in two dimensions, but it always has to be compared with respect to time, because length and distance, if they are moving or are varying, they can only vary with respect to time, not any other quantity. Now some mathematicals and matrices forms are there, row and columns and system. Now a practical example is shown here. One-dimensional system. A single dot is represented in which row and column coordinates are taken to be 0. If we are drawing on a graph, it can be just the center point of origin. So if on a graph we point a circle or make a dot on the origin, it will have any coordinate or in magnitude. So its magnitude, its 1 is shown exact origin. Now a little displacement is shown, magnitude is still 1, but here we see the diagram is displayed on the negative y-axis. So here the z coordinate has taken some value here. In the original it was 0, but now it has taken some particular values here. Now Gaussian noise is shown. Some practical examples are mentioned and its discrete function in 3D are shown. Two magnitude axis, third height, and all drawn with respect to time, that is the 4 dimensions. Now here a natural colored image is taken. So there we can see a lot of red peaks, yellow peaks, and magenta and so on. So they are color-wise categorized with the depth. For example, if we have scaled or categorized the red spots to be of lesser depth, and if it's showing a human face, then red dot can be a jawline or a nose hollow portion, and the drops which are showing a high projectile, they can be chin or your cheeks, and so on. Through coloring, we can 3D picturization of a face or any other visible thing. For example, a natural image is shown and its spectral form in X, Y, and Z axis with respect to time are shown, and this is a spectral density diagram. Okay, now till now we have dealt and seen what are signals, how are they basically mathematically represented. Now, since we have to deal with both system, if signal is there, then it's but natural that it has to be taken as an input to a particular system and resultant output will be there. So here we are trying to classify a system, and there could be numerous examples as far as signal processing or signal implementation is concerned. For example, DNA sequence analysis, picture compression, JPG, PNG, and so on. Net security, which is mark by encryption and watermarking, and several other things, all related from medical industry and even military functionality. Now here we have taken a very simple approach to our system in which our input is there. System, it is a closed loop system which output is again used for analysis and correction of system. So it's called a closed loop system. Now we are going to begin with some mathematical portion of signals. So we have categorized various parts, for example, continuous, analog, periodic, aperiodic, energy, and power. So basically now we are moving from generalized to a very customized mathematical portion, which mainly of interest is of picture or signal processing field people or image processing field people or signal analysis. Here we are taking a pictorial view and side by side a diagrammatic view of pictorial mathematical view of a signal. Continuous time and discrete time. Now continuous time takes continuous value of time at its in space and time. But discrete signals, though moving like a time, but take only integer values. So in both diagrams, you can clearly see that pictorial representation is a continuous set of diagrams. But when you talk about discrete values, they are being seeing a certain gaps here. These certain gaps show a loss of information in terms of discrete analysis, which can be dealt through fast sampling, which we will study later on. Now here basically a comparison between analog and digital signal. Now this diagram, we are trying to emphasize how an analog signal is digitized. For example, when we go to a market and we see in a normal shop a digital weighing scale, so we wonder how this actually works because we are measuring a physical thing through a digital measurement. So we sometimes wonder how an analog signal, how we are able to make machine understand that if this is 2 kg, a machine who deals in binaries in ones or zeros. So basic challenge is to make machine understand how this 2 kilo is to be shown to a customer as a 2 kgs. We all know that machine does not have its own brain. So we have to customize certain sets of hardwares as per our need to make machine work like an analog weighing scale is merged. Now in digital, we are dealing with 1-0 sequences, and a machine bits and works in terms of bits. Earlier, microprocessor and microcontrollers, there were 4 bits, then there were 8 bits, then 16 bits, and so on. Now we have a 64-bit system, and some supercomputers are working on a 128-bit system. So we are not going to detail about the bits, but we have to generally physically understand that how bits contribute to a costing of a machine. If we increase the bits, the accuracy of machine improves, but that improvement comes at the cost of high cost of that product. So we have to find a midway and scale the cost of the product as per need. For example, if we are doing a chemical calculations, which we require in terms of milligrams or even micrograms, then accuracy is of high weightage, and so we will need high bits machines to give accurate calculations. For example, if we are doing a normal weighing, then such large accuracy is not required. For example, if we using a machine for chemical reactions of chemical experiments or even chemistry experiments, we will try to go for 64-bit machines. But if we are using a normal purchase shop we find in our localities, then we can easily compromise and go on a 16-bit or even a 32-bit scale. Because if we are weighing, for example, a flour bag or even a wheat bag, which weighs upon 20 to 30 kilos. And if accuracy can be varied, for example, 30 kgs, if it's actually 30.01 kgs. So that's the difference of 20 gram. So we can easily make a compromise between that values. So here, basically, we are seeing analog signal, how it is converted to a digital value. Here we are showing a amplitude on, there is a vertical dots. So basically these amplitudes are divided. Now here we see 6 or 7 divisions, which generally represents about 8-bit machines. If we do more divisions of that particular amplitude, then accuracy of our measurement will be declared. More divisions mean more bit will be needed. So this is a basically overview of how the digitization of an analog signal is done. These are two basically representation of a analog signal and continuous time signal. Now there is a discrete time representation, which I have already mentioned. The dotted line is showing the continuous time representation, and this bubble and straight line is showing the discrete. So discrete comes with a disadvantage of missing the data between two integer values, which can only be compensated through high sampling rate. Now there is a summary of our digital and analog signals in terms of real, integer, and continuous value through space, time, and space. Now we are basically dealing with a mathematical portion of periodic and aperiodic signals. Periodic signals are which we are defined for a certain set of intervals. For example, it is shown ft plus t naught equals to ft, means t naught is a repetitive time period which needs to be repeated through time. One more thing to note is that if a time representation is to be made, it has to be made from minus infinity to infinity. A signal cannot start from exactly zero. Any physical signal or real-time signal cannot be start from zero. We generally see in our books that signal starts at zero. But that's for our sake of mathematical computation. In the real world, signal flows continuously. And if a signal is continuously flowing through time, we cannot mark any starting point because it's a infinite flow of signal. It has to be from minus infinity to plus infinity. We take a particular time slots of this, out of this infinite time sequence for the sake of our mathematical calculations, and that's it. Signal always flows from infinite to plus infinite. Now there are various examples are shown for periodic and aperiodic signals. Now a very interesting case is there, causal and non-causal signals. And its mathematical definitions is that a causal signal is said to be causal signal if its value depends on present and its past value. And non-causal signals are those signals where present value depends on future values. Now, in real world, in the world we live, nothing is non-causal signals. All real-time signals we see, we perceive, and even life of our human being is a causal system, because when a person sees another person, he can perceive that person at that present time or in the past time if he had or she had known that person earlier. What a particular person can do or will do or capable of do in future, we cannot predict or cannot suggest. That's why at the present value of a person cannot be predicted in future times. And that's why all real physical signals are always causal signals. But a non-causal signal can be created virtually. How? For example, if we record a cricket match and if we see a particular section of match, we have already seen the match live and now we are seeing the recording of a particular match. So at any past value, we can predict what the result of that match will be done because we have already seen that happening in a real time. So that's why it is said we can imagine a non-causal system, but not in a real world, only in the virtual world, because futuristic implications, or if we try to say in terms of machine, it could be artificial intelligence, predictive machines we have seen only in the movies. In real world, even quantum computing has not been achieved to predict human behavior on its present or its past, that how will a person perform in the future, because a human is a complex being and its nature keeps on changing, and even his past history is nothing to do with future behavior. A person can change or it cannot change, but the machine or even a human cannot predict. So real-time signals or everything we see in this world or in this universe are always a causal signals. Nothing here in physical are non-causal signals. So that's the practical implications. And that's a mathematical representation of things. And now we are moving inward into mathematical details. For example, this is an even signal. Even signals are always symmetrical around the y-axis. If we fold a particular diagram and if it's completely superimposes upon each other, then it's a even signal. And if it doesn't, then it's a odd signal or anti-symmetrical signal. Now the decomposition parts are shown, mathematical representation of even and odd sequences. Let's skip even and quotient. Now here practical approach of a signal is concerned, deterministic and probabilistic signals. Uh, Actually, the physical signals, for example, if we try to measure a signal that comes from a vibration of a rock, that's a random and a complex signal. Nothing mathematical exists in this world that can clearly define the vibration coming from a rock. So this concept deals with a random and complex variable signals, how close we can compare it with a standard mathematical forms. And if it has to be run in a finite sequence, then we have a tool known as Fourier transformation and Fourier series conjugation, which deals with random and non-deterministic signals, means signals which do not exist in a standard mathematical form. Standard mathematical forms are triangular signals, impulse signals, sawtooth signals. These are signals which are defined mathematically. But if we see the real world signal, for example, a wind blowing, rustling of winds, nothing ever shows like a deterministic mathematical signals. So we remodify and try to resample it as close as possible to the mathematical form, because even the high computation supercomputers cannot exactly model real world signals. Uh, this is a real comparison is made. For example, if a particular input we receive from a vibration of a signal is like this, that is the bottom one. So this is not a standard form which can be represented in a mathematical way. The closest resemblance which can be made in the bottom signal is a sine wave. So we try to resample and remodify the bottom signals, so make it as close as possible to this real-time mathematical form, so we can do all the mathematical calculations. Now, as we have defined that signals that exist in real world are actually infinite length signals. So here we try to define, for the sake of mathematical calculations, that how can we range. Basically, it is used to define a system in terms of stability. When we use an infinite length signals, we basically define in terms of stability. So if we have a system and if we have to redefine in terms of stability, then when we talk of finite and infinite length intervals. Uh, Now a very general topic is mentioned, like a size of a signal. So if we as a person has dealt with digital signal oscilloscope or any messaging instruments earlier, sometimes the signal measured are large, so we have to scale down. Now to scale down a real world signal, we have to monitor various parameters. For example, its repeatability has to be confirmed. For example, if how many time periods it's repeating itself, whether noise is there, where signal gap is there, where if in terms of a discrete, then how data loss can be compensated. So all these factors has to be kept in mind. Now, various classification of made in terms of energy and power signals. So a signal at a particular time cannot be both energy or power. If energy calculation comes to be finite, then it's an energy signal. And if it's power calculation comes to be finite, then it's a power signal. So basically mathematical difference we see in energy and power signal. Energy and power both are taken in infinite time sequences. Sorry, energy is taken in infinite time sequence, whereas power is taken always as a limited value and always talks about the limited or a fixed time period. So the basic difference is energy and power is that energy is always calculated on an infinite time scale, whereas power is calculated always on a finite time scale. So in a general way, we can say that all real world signals are energy signals. Now there is a mathematical representation which shows signal noise and signal noise ratio. Uh, now the basic energy signal operation is mentioned, in which signal is shifted in past or future. So it basically shows a causal and non-causal behavior of a system. For example, if we see a second diagram, if it's shown that Ft is shifted in the left by Ft plus t, and if it relates to the causal interval, then if time equals at the tip of this triangular at to be taken to be 1 second. For example, at time equals to 1 second, magnitude is 1. If we take the shifted version of the signal, that for the same time 1 and capital T equals to, for example, 1, then same magnitude will occur at time equals to 2 seconds. So magnitude 1 exists at time equals to 1, whereas in the second diagram, magnitude 1 exists as time equals to 2, which means that present values depending upon future values. So basically, it shows that it is a non-causal system. Now, some the expanding and scaling of signals are mentioned. For example, this signal length is shorted, and here the signal length is expanded. So it's the user expanded version, and this is the compressed version. The mathematical representation is there. We will not go into many detail. Now, very interesting concept is there is a mirroring or inversion of signals. Now, generally, inversion of signals, we see that image is inverted. But when we terms of signal and systems and in terms of mathematicals, the inversion is always done through vertical axis and about the point 0. These are two basic conditions for mirror imaging, which we may make mistakes easily. Example, we take the mirror image around the y-axis, but we forget to rotate that figure around the 0. We always tend to take end-to-end values, which is wrong. Image has to be rotated about the point 0 and about the vertical y-axis. That's a parameter which we need to take care of. Now, this is the general representation, which takes all the three parts: shifting, scaling, and inversion. For example, B is negative or positive, which result in advancing or back sequencing of signal. The capital A dependence value is greater than or less than 1. We deal with scaling or compression of signals. And that same A, if its sign is negative, then with the scaling and compression, it will also show inversion or non-inversion signal. Now some standard mathematical signals are represented. These are unit step, uh, continuous time, and discrete time. Now mathematical combinations of ramp and unit step is there, and its mathematical sequencing is resulted. Impulse is shown here, and some basic properties in terms of mathematical formulas. Now various mathematical relations are shown. Here it is shown unit impulse, its relation with respect to discrete time impulse function. Now sinusoidal function can always be represented into Euler's form, which we are showing here. Euler forms is represented in terms of e to power j theta, and its Cartesian representation is cos theta plus j sin theta. So a sinusoidal function can be represented in terms of exponential functions with the help of Euler identities, which is clearly shown in this Euler's relation. Same goes for continuous time and same goes for discrete time. It can be easily represented. Now Laplace transformation of that same form is there. Now some standard functions are here mentioned: exponential, decaying and rising function, sustainable sinusoidal function and cosine function, damped decreasing function, exponential rising function. Now here whosoever students have studied networks and control, they clearly know that is a representation of real and complex form, and it's divided into right and left half. Left half roots positions talk of stability, and right side's root position talks about non-stability of systems. Now, basically, for the academic point of view, we see in our syllabuses. Basically, we deal in the earlier courses of undergraduates in two dimensions, and as we move on in curriculum, in the 7th semester or in some courses in the 6th semester, we see the basic and major and practical implementation in form of 3D sequences and three-dimensional resourcing and planning of image processing. Now, mathematical modeling of system is made here, in which many input functions are shown. These input functions can be a vision signal, it can be a signal coming from a heat sensor or light sensor or sound sensor, or even a sound signal, and these are related outputs. So system can be anything and input signals can be anything depending what we are trying to achieve. Now systems are basically clarified in single input, single output, and multiple input, multiple output. In this, only one input is there and one output is there. In this, many inputs are there and its related outputs are being shown. Now, if we talk about time sequences, then a transient response or a time-based response of a system is generally divided into transient state and steady. Transient state deals with immediate on and on of system, and steady state deals with a long time lapse after the transient state has passed. So basically in the mathematical form, these are shown here, zero input response and zero state response. Some graphical representation and causal and non-causal values are mentioned here. Now a system representation in terms of transfer function is mentioned here. Uh, that's above are shown of a continuous time, and that below are shown of a digital value. Example, a real world analog signal is taken and it's sampled and digitized into digital form. Then digitally it is processed in terms of discrete input and discrete output and reconverted in terms of analog signals. So this is the basic conversion, which is in addition it is used. Now various properties of additivity and homogeneity exist in a linear system, which we again here this is a mathematical extension of whatsoever we are talking about. Now causal and non-causal implementation of system in terms of mathematical formulas. Linear discrete form is that linear impulse modulus forms are there. Now concept exists in which now a concept exists which we know as convolution, which transforms or in fact folds a dimension into three-dimensional space. It rotates, it inverts, and it's reinverts. For example, original diagram is shown that in sequence is tilted downwards, in other it is tilted upwards, and in third it is rotated and tilted both. So convolution integral helps to find all the 3D variation of a particular signal in a real time. Matrix perspective is shown here. For example, this is the original matrix. Then it is folded along the x-axis. So CBA, FUD, and IG. Then it's folded upon the. If we see clearly, it shows a cubic with cube blocks, which we have to color matches. It follows the same pattern. So convolution shows the all set of integrals and revaluation of every sampled space. This is all mathematical portion, how the convolution is done graphically. It is done in terms of mathematical signals. So guys, that's it for today. And in the next coming sequences, we'll be further